Hello and most welcome to 1252 of the Heidegger series. And it's still very climate, summer-like almost, the climate. It is just beyond belief. So you see some of the trees still have their leaves on. So we haven't experienced any heavy winds either, which is even more mysterious. We will continue with One Single Universe by Smolin and Roberto Unger. It's 1252 here, as you can see. There we have Roberto Unger and Smolin. The latter, a physicist, renowned, most famous, the former philosopher, economist, sociologist, and even politician. Nice mixture. We were at page 100, and let's see here, 115. And here I wonder what happened. Oh, still workable maybe. Oh, I just put it on the wrong. The last sentence from 1251, or it was even earlier than that. We have reason to think, I later argue, that nothing remains outside that reach. Moreover, we know already that many aspects of our universe, for example, its chemical constitution, could not have existed early in its history. Even the most fundamental constituents of nature and their intersections must have been different in the early hot and supercondensed universe. If everything was different structurally, how could the regularities of nature have been the same? We would have to suppose that the same structural transitions recurred many times before and did so under the governance of laws, symmetries, and constants that remain themselves immutable. This idea, however, is a metaphysical leap, unsupported by anything in our knowledge of nature. Other than the stability of the regularities that we observe in our cool-down universe, and that we infer to have been stable down to relatively early periods in its history. it is more economical and more in accord with explanatory practice in science that are accustomed to deal with the mutability of their subject matter. Such as the earth and the life sciences, to think that the regularities evolve together with the structures. The non-cyclic or cyclic variant of the thesis of succession, with its insistence that everything, including the structures and the laws, changes sooner or later, must also overcome two major obstacles. In addition to the challenges presented to all variants of succession. The first obstacle is the undeniable stability of the regularities and constituents of nature in the cool-down universe that has been, until recently, the sole subject matter of cosmology and physics. If we come to think that these constituents and regularities have changed in the past and may change again, we must reconcile the idea that they are mutable with the fact that they have been stable. They can be both mutable and stable. Very important to remember. The second obstacle is the riddle resulting from the idea of their mutability. Which we call the conundrum of the meta-laws. If the laws and structures evolve jointly, it seems that in accordance with this way of thinking and with the continuity of causation, that co-evolution must be neither law-governed nor uncaused. To address the conundrum of the meta-laws is one of our main goals in the subsequent arguments of this book. arguments for the singular existence of the universe. I now outline arguments for the singular existence of the universe, as well as for the non-cyclic succession of universes. And against the plurality of universes. I refer to the notion of plurality with emphasis on the form of this notion that has recently acquired influence. The one that I described in the previous section as divergent rather than parallel plurality. That is now commonly known as the multiverse. These arguments have different characters. Some of them are negative, directed against the idea of plurality. Others are affirmative, in favor of the ideas of singular existence and of non-cyclic succession. Some invoke a conception of what the relation between theoretical speculation and empirical validation can and should be like in cosmology. Others appeal to claims about the most persuasive interpretation of past cosmological discoveries. Others yet emphasize the implications both of the views that I propose and of those that I criticize for the additional matters that we address in this book. The reality of time and the role of mathematics. Some of the arguments touch on foundational issues in science. Others are subsidiary to these basic claims. Despite their heterogeneity, however, the arguments connect and overlap They exhibit a point of view that should be judged by the fecundity of the agenda of theoretical reasoning and of empirical research that it may inform, as well as by the merits of its particular propositions. The rest of this chapter explores the implications of this way of thinking about the solitary character of the universe for a number of problems that are important to the present and future of cosmology. One, the argument from the non-empirical character of the multiverse idea. Plural universes are in principle beyond the reach of empirical inquiry. They resist empirical investigation because they are not and have never been in causal contact with our universe. They intersect no light cone crossing the history of our universe. They share no history with us. The impossibility of confirming or disconforming their existence reduces them to a fabrication. Reliance on any such fabrication represents a major flaw in a scientific theory. To establish this point, it is important to exclude from the idea of plurality branching, bubble, or domain universes that may have resulted, just as black holes do, from the events in the history of our universe. Such universes should be considered instances of succession rather than of plurality. Our universe may not enjoy causal contact with them now. Nevertheless, there was once a time when it did. Causal communion must be defined historically rather than statically. Another example of the historical character of basic cosmological concepts. We may not be able, with our existing equipment and powers of observation and stimulation, to take empirical advantage of these past episodes of historical intersection between universes, or among parts of the universe that later fell out of causal contact with one another and with us. Nevertheless, they are in principle accessible, if not now, later, and if not directly, indirectly, to empirical study. It is a connection over time that provides the criterion by which to distinguish a universe, whether singular or one of many. Notice that nothing in this notion of causal connection assumes action at a distance. The suggestion of which led Einstein to reject Mach's principle. The suggestion of which led Einstein to reject Mach's principle. Very important to remember. After having embraced it and named it, yes. Such action is nevertheless now admitted in thinking about fields and quantum entanglement. The local inertial field is completely determined by the dynamical fields of the universe. But it is not determined by the matter content of universe without regard to the shape of those fields. The net of causal connection must remain uninterrupted, even if at a distance. Everything in the universe must influence everything else through connecting links or mechanisms for transmission of causal influence to occur. The influence, however, may be historical it then becomes a major concern of cosmological or physical theory to supply an account of such links or mechanisms that can be put to observational or experimental test. What this criterion of the separate existence of a universe does presuppose is the continuity of causal connections. Whether or not they assume law-like form, together with the reality of time as a condition of causality. We cannot affirm the identity of a universe by viewing it without regard to its evolution. We can affirm it only by seeing it in evolutionary context, which is to say, in time. What was in causal communion may at some point cease to be in causal communion. Whether such a division does or will occur is not something that can be known a priori or confirmed on the basis of theoretical considerations. It depends on how the universe, in fact, evolves, and in particular on the nature and rapidity of its expansion. That branching bubble or domain universes do not deserve to be considered instances of plurality is shown by the absence of any clear distinction between the idea of universes branching out of a single universe and of parts of a universe no longer in causal contact with one another.
that parts of even the observed region of our universe cannot now be in causal contact is a widely accepted tenet of the contemporary cosmology. Helping motivate the theory of cosmological inflation. The unity of our universe is established by causal continuity over time, not by inclusive causal contact at all times. Plurality, according to the nomenclature proposed in the earlier section, can take the form of an idea of parallel universes, all exhibiting the same regularities, laws, symmetries, and constants, or of divergent universes, each of which displays different regularities and structures. The idea of divergent universes goes in contemporary cosmology under the name multiverse. There is no reason to uphold the idea of parallel universes. It combines an absence of empirical validation or of susceptibility of empirical challenge with a lack of explanatory function. It is therefore unsurprising that it attracts little interest among present-day cosmologists. By contrast, the idea of divergent universes combines the same lack of empirical support or vulnerability with an explanatory role. This role, however, rather than providing a basis to accept it, supplies additional reason to doubt it. The driving motive to postulate many divergent universes is to convert an explanatory embarrassment into an explanatory triumph. The explanatory embarrassment is the failure of the most influential variant of contemporary particle physics, string theory, to apply narrowly to the universe that we see rather than applying as well to countless universes that we do not and cannot now or ever observe. Even if we impose on perturbative string theories a long series of constraints, no more than a tiny portion of them apply to the observed universe. We can tell ourselves, so long as we are willing to accept the idea of plurality, that each of the inapplicable theories is realized in one of those unobservable universes. By such special pleading, we pretend to turn a failure into a success. As the setback to prevailing ideas were a taint to be disguised rather than an opportunity to be seized. It has been argued in favor of the multiverse idea that the particle theories suggesting this idea have been successful at many other predictions, and that therefore that prediction of a multiverse deserves deference. This defense, however, is doubly defective. First, it confuses the extraordinary predictive success of the standard model of particle physics. Which bears no relation to the multiverse conception, with the claims of string theory, which has had a more questionable record. Second, and more fundamentally, it abuses the idea of prediction to postulate the existence of universes on the ground that each such universe realizes one of a vast number of possible states of nature. Countenanced by the mathematics of a physical theory is a prediction only in a contrived sense. If the postulated entities cannot ever be observed, and no trace of them even indirectly found, the application of the prediction has lost touch with what prediction has meant in science. We go even further in redefining riddles as solutions and failures as triumphs when we combine the multiverse notion with the practice of anthropic reasoning. Oh my God, he's brilliant. Only a few of the possibilities established by string theory in particle physics approach the realities registered in the observed universe. In fact, no version of string theory has completely reproduced the standard model of particle physics, which has been amply confirmed by observation and experiment, or even its supersymmetric extension. All the other equations and solutions generated by string theory must describe the inaccessible universes in which the realities to which they would apply are supposedly realized. In each of these universes, the regularities are the one that conform to equations and solutions not realized in our universe, and must therefore differ from the laws, symmetries, and constants observed in our cool-down universe. By this combination of moves, we seem to dispose of the difficulty presented by the massive undetermination of reality by theory in some of the variants of particle physics now commanding the greatest support. We do so, however, only at the cost of devising a research agenda that weakens the vital connection between theoretical insight and empirical discovery. The opposing idea of the singular existence of the universe conforms to a tradition of several centuries. It avoids resort of metaphysical fictions. However, its conservatism turns out to be revolutionary. It denies us a facile solution to connected and major conundrums. As a result, it helps open up another little explored way of addressing those same puzzles, a way giving a central role to the ideas of the reality of time. And of the mutability of the laws of nature. These ideas in turn compel us to reconsider the relation of mathematics to nature and to science. Such a turn invokes no fantastical entities. Many of its aspects cannot yet be subject to observational or experimental test, while others can. None of its claims, however, is in principle and forever immune to empirical challenge. Two, the argument from the preference for a view making it possible to begin answering the question, where do initial conditions of the universe and the laws of nature come from? The idea of a multitude of universes having no causal contact with one another and no shared history makes it impossible to answer the question. Where do the laws and the initial conditions of our universe come from? Or more precisely, the idea of plurality leaves open only one answer to this question. They are one of the countless possibilities envisaged by a fundamental physical theory that also accommodates many other possibilities. All the other, this is grand, all the other possibilities, the ones not realized in our universe, are realized in the other universes that we can only postulate, but never ever inspect, even indirectly, or later, or even sooner.
This deserves a cup of tea.
Let us generalize the argument without regard to the specific content of the multiverse idea. There are in principle three approaches to the question of the basis of the laws and other regularities and the initial conditions of the universe. The laws and initial the laws and initial conditions just are what they are. They are a primitive feature of nature. They cannot be inferred from anything else. Then the regularities of nature are like surprising singular events, except that what is not only surprising and singular, but also beyond the reach of further explanation, is the universe itself. Science then presents the apparent disorder of the universe under the semblance of regularities. This representation, however, only postpones the confrontation with brute factitiousness. The phenomena are to be explained by the laws, symmetries, and constants, together with unexplained initial conditions of the universe. At the next step of reasoning, however, both the laws and the initial conditions remain unexplained. B. The laws of nature and the initial conditions of the universe can be inferred from some higher order set of abstractions. A set of laws of many possible universes, or an account of why only the features of this one universe of ours are possible because, for example, only they realize in the richest and fullest way the potential of being, sein. This approach expressed in the thought of philosophers as different as Leibniz and Hegel, and I'll have to add Heidegger, always amounts to a mystification of one kind of another. It seeks to make the brute just soness or factitiousness of nature appear to vanish under the spell of rational necessity. The relative ease with which the surprising features of the one real universe can be made to follow from metaphysical a prioris discredits such efforts at wholesale retrospective rationalization. A variant of this approach is the idea that every structure conceived by mathematics is expressed in some universe as its laws and symmetries. At the limit, each such universe is one of these mathematical structures. Because the realities that we observe in our universe embody only a tiny part of these mathematical structures, all the other structures must be embodied in other universes. The rationale that is real is mathematics. Taken to the hilt, such a view dismisses the reality of time and dispenses with the concept of initial conditions. C. The laws and initial conditions can be explained historically. Like everything else in nature, they are the outcomes of earlier states of affairs. To be sure, the appeal to historical explanation fails to exempt us from the problem of factitiousness. Ultimately, that the universe and its history, or the universe viewed historically, just happens to be one way rather than another. This third approach, nevertheless, has several advantages over the other two. A first advantage is that it opens an agenda of empirical inquiry closely connected with the most important discoveries that cosmology has made over the last century. All these discoveries have to do in one way or another with the aspects of the history of the universe. They provide incitements to the continuing transformation of cosmology into a historical science. That transformation remains incomplete so long as the laws and initial conditions fail to be viewed historically. A pressing task is to find ways to render these questions amenable to observational and experimental research by considering the empirical consequences in the present universe of alternative conjectures about its early history, or about the history of previous universes. A second advantage of this approach over its rivals is that it enables us to delay confronting the factitiousness of the universe, that it is what it is rather than something else. And that what it is cannot be inferred from any higher order rational necessity. Science is powerless to determine the ground of being, why there is something rather than nothing, or why, to take a thesis that we develop in this book, space may be emergent, whereas time may not be. It matters decisively, however, to science, whether the confrontation with the brute just soneness of natural reality, undisguised by the pretense of rational necessity, takes place early or late in a course of scientific inquiry. From the perspective of the interests of natural science, the later it takes place, the better. The dialectic between theoretical imagination and empirical study can then advance over a broader field and expose itself on that field to the surprises of experience. A third advantage of this approach in relation to the alternatives is that it enables and requires us to dispense with any appeal to the idea of the infinite. It replaces the infinite with history. At the beginning of the 20th century, the most influential interpretation of the field equations of general relativity argued for an infinite initial singularity at the beginning of the universe. It was widely recognized that the invocation of the infinite revealed a breakdown in the application of the field equations. To conditions in the earliest history of the universe, rather than providing an account of a physical state of affairs. Here, as always, the infinite is a mathematical idea rather than a reality present in nature, a cosmology insisting that causal continuity between the universe and its possible predecessors may be stressed rather than broken, need make not invoke the deus ex machina of the mathematical infinite. Both cyclic and non-cyclic views of succession may enjoy these three advantages. Non-cyclic views, however, enjoy them more fully than do their cyclic alternatives. The cyclic views of succession suppose that the regularities of successive universes remain the same. The initial conditions of each universe must therefore also either be the same or represent a stochastic instance of the states of affairs that such laws of nature make possible. As a result, any opportunity to explain why these laws hold rather than others, as well as why these initial conditions occur rather than others, is drastically foreshortened. An additional difficulty is that the known laws and symmetries of nature fail to account for the initial conditions of the universe. These conditions are in fact highly unlikely in a world described by those laws and symmetries. It is then hard to see how a cyclic view can adequately address the task of explaining the initial conditions in early universes or in earlier states of the present universe. The enigma, rather than being dispelled, would be multiplied many times over. By contrast, a non-cyclic view of succession enables us to ask how the laws, symmetries, and constants of nature and the initial conditions of the universe came to be what they are, and to seek answers in the history of succession. Under such a view, we are freed, as I next argue, from the need to distinguish between the history of laws and the history of initial conditions. We must reject any such distinction if we are to complete the transformation of cosmology into a historical science and avoid the first cosmological fallacy. That is, resort to what we call the Newtonian paradigm. The question remains whether we have more reason than not to think that there is such a history of the regularities of nature, despite their remarkable stability in the cool-down universe that we observe. Several of the following arguments imply that we do. 3. The argument from rejection of the first cosmological fallacy. The ideas of the singular existence of the universe and of non-cyclic succession allows us to avoid the illegitimate cosmological application of the Newtonian paradigm. All major physical theories in the history of modern science make use of the Newtonian paradigm. Classical mechanics, statistical mechanics, and quantum mechanics, and special and general relativity. The defining feature of the Newtonian paradigm is the distinction that it draws between stipulated initial conditions and the changeless laws governing changing phenomena within a configuration space, bounded by the initial conditions. Throughout this book, we argue that the Newtonian paradigm has no proper cosmological use. The distinction between laws of nature and stipulated initial conditions cannot be maintained when applied to the universe as a whole, rather than to patches of nature or to regions of the universe. A multiverse cosmology may appear to mimic the conditions for the application across the multitude of universes that it postulates. Of the Newtonian paradigm properly applied only within a universe. The analogy, however, is superficial and flawed. For one thing, in the proper use of the Newtonian paradigm, which is its application to parts of the universe, only the initial conditions change from one instance of the practice to another. The supposedly timeless laws remain always the same. However, in the multiverse version of plurality, the only variant to have any theoretical interest and influence today, the regularities as well as the initial conditions differ among universes expressing states of affairs allowed by the motivating theory that are not manifest in our universe. For another thing, in the proper use of the Newtonian paradigm, what is stipulated initial condition for the purpose of one instance of the explanatory practice becomes an explained phenomenon for the purpose of the next instance. It is as if the moving searchlight that defines the configuration space, and thus the distinction between what is stipulated and what is explained, illuminated all of nature piece by piece. No opportunity for such an iteration of the practice exists under the multiverse conception. In that conception, each imaginary universe is a complete and closed entity, bereft of causal contact with any other universe. The replacement of plurality by succession and the subordination of structural to historical explanations open the way to dispensing with the cosmological application of the Newtonian paradigm. If there is only one universe, in parenthesis with a qualification of the existence of branching universes, as well as of the existence of unobservable parts of our universe, and succession takes the place of plurality. We need no longer, with regard to the universe and its history, try to distinguish unexplained initial conditions from a configuration space of law-governed changes. The whole cosmological evolution, without any such distinction, becomes the topic of explanation. The realities to be explained, not all at once, but step by step, include what the Newtonian paradigm distinguishes as initial conditions, law-governed phenomena and explanatory laws. Once again, the non-cyclic variant of succession enjoys, in these respects, an advantage over the cyclic one. The regularities of nature cease to be eternal bystanders to the history of the universe or of successive universes, and become instead protagonists in that history. I argue later in this section and in this book that we have independent reasons to regard the regularities of nature as susceptible to historical explanation. Four, the argument from the compatibility of the associated ideas of the singular existence of the universe and of non-cyclic succession with cosmological inflation, and from their irreconcilability with eternal inflation. The standard cosmological model faces a number of problems that have to do in one way or another with the need to explain how the observed universe can be flat, homogeneous, and isotropic. When it might be expected to be highly curved and inhomogeneous. Prominent among these riddles are the so-called horizon and flatness problems. I think I'm going to take those up because they're very interesting. There's going to be a parenthesis, and I will read the footnote. The horizon problem has to do with the relation between features of the observed universe and the lapse of time required by the physical processes needed to produce them. At the time that it has become conventional to call decoupling, when the atoms became stable and light could travel freely, the universe was already and has since remained remarkably homogeneous and isotropic. It everywhere exhibited and exhibits the same temperature to high accuracy and the same spectrum of small fluctuations in density. Much too little time has elapsed between the cosmological singularity, as conventionally viewed, for all the regions of the universe at its then size to have been in causal contact. Nothing that we are able to infer about the initial conditions of our universe, without making arbitrary and ad hoc stipulations, can account for such a surprising result. Restated, the horizon problem is that models of the early universe based on general relativity and assuming only the matter now known to us fail to explain uniformity of the cosmic microwave background. The parts of that background, vestiges of the earliest universe, could not have interacted by the time they are observed to be everywhere in equilibrium at the same temperature. The flatness problem is that in our universe, light beams neither converge as they would under general relativity if space were positively curved, or diverge as they would under the same theory if space were negatively curved. The flat universe must have begun close to the naturally improbable circumstance in which the expansion rate and the energy density of the universe compensate for each other's effects. So horizon problem and flatness problem. So I will leave a footnote there. These problems played a major role in motivating the conjecture of cosmological inflation. of a super rapid expansion early in the history of the universe. Instead of a standard causal interaction resulting in a convergence of temperatures and of densities within the expanding universe. There is supposed to have occurred, according to this doctrine, an explosive ballooning that scaled the universe up. The scaling up would then have produced what could not have been achieved by a causal interaction for which there was not enough time. Proponents of cyclic succession have often claimed that their theories offer a solution to these problems without invoking cosmological inflation. For which they have argued there has been, or at least very recently, no direct evidence and only conjectural mechanisms. Theories of succession, whether cyclic or non-cyclic, would offer such a solution by extending back the time horizon for setting the pertinent features of the observed universe. Its fundamental homogeneity and isotropy, its local and detailed inhomogeneities, which is indispensable to the formation of the observed celestial bodies, and its flatness. The premise to such solutions is that the properties of the universe at decoupling should be understood historically in the light not only of what happened between the earliest formative events and decoupling, but also of what took place before those events in the prior or pre-translational chromatic universe. Once we admit succession and redefine the cosmological singularity as a moment at which temperature and density were extreme rather than infinite, and as an incident in a longer history rather than an absolute beginning. There may be enough time for the parts of the universe to have become homogeneous and isotropic. Thus, if cosmological fails ultimately to be confirmed, no difficulty would result for either cyclic or non-cyclic views of succession. Suppose, however, that evidence for cosmological inflation mounts. A fundamental difference exists between the implications for cyclic and non-cyclic succession. The ekpyrotic version of cyclic succession, as proposed by Steinhardt and Turok, would then be unequivocally falsified, if only because it supposes the present universe to have begun in a low energy state, irreconcilable with the inflationary view. The many proposals of succession that have made no such assumption of an early low energy state contradict the inflationary picture in less obvious ways. If we refuse to understand inflation as a recurrent event, determined by timeless laws, as it might be represented under the theories of eternal inflation, we need to comprehend it as triggered by the special and exceedingly improbable initial conditions of our universe. It thus fits easily into a historical account of the universe, one that does not suppose that we can infer their history from the laws, not at least from the known laws. Such an approach to inflation would demand attention to the question, from where do the initial conditions of the universe come? If they are not randomly generated within a multitude of mathematical probabilities, they must be explained by what happened before. We must, that is to say, account for them historically. Hooray, yes! Another strike. If such evolution is to be explained by immutable laws, they should be laws that generate over and over again the same initial conditions. Such are the regularities that theories of cyclic succession, which includes the ekpyrotic theory and Penrose's conformal cyclic cosmology, presuppose. Carried to their logical extreme, these theories dispense with the concept of initial conditions of the universe. Everything for them resides in the laws. They see no need to speak of initial conditions as distinct from the laws and their consequences. However, the regularities that can explain the initial conditions of the universe resulting in cosmological inflation could not resemble the laws, symmetries, or supposed constant of nature with which we are now acquainted. Otherwise, the initial conditions of the universe would not seem as extraordinarily improbable to us as they do. They seem improbable because they are not the expected outcome of the regularities with which we are familiar, those that apply to the cooled-down universe that we observe. No such antipathy opposes the combination of the ideas of the singular existence of the universe and of non-cyclic succession to cosmological inflation, as distinguished from eternal inflation. So it's deep thinking going on here, it is pointing to a grandiose mistake. And heck, we are used to this. Nobody would reject or have any criticism if I say I'm going to do an experiment in a closed room like this one, and then I'm going to expand it to cover the whole universe. And then I'm going to invent initial conditions we can never know. Implicitly, they are actually hinting to that the conditions are outside the universe. If we can't know them, they are outside of space and time. And by this theft of knowledge or obscuring of knowledge, the laws are constructed, permanent laws. But interestingly enough, with the universe with only laws, laws cannot be explained how they came about, because they certainly are not compatible with this present cooled down universe. Not at all. There is no probability whatsoever. And that is an interesting reason for why the initial conditions and the Big Bang has been proposed. Is to cover why the laws are like they are. Otherwise, there's an incredible mystery that goes beyond horizon and flatness problems, which are also adding, I would say, to the mystical flavor here of the classical paradigm. It simply doesn't work. But we are so used to it. And we are so used to the idea that we can expand every experiment to cover the universe. It became natural to us. We just call that science or model. And the one is quite all right. It's 100% okay, as long as you're outside the laboratory to say, this model covers what happens in the laboratory, because you are literally outside. But you're not outside here anymore. And there is nothing of an outsideness to the laboratory of the universe. This needs to be understood. Otherwise, you'll be victim for eternity of this closure of the mind, which is the old paradigm, or whatever you call it. I would say mistaken understanding of knowing. This is a blockage of knowing. Here no longer can any knowledge come about or be reached, because we mishandled it and we placed understanding outside of our reach. Knowledge became disembodied in an incredibly literal way, literally disembodied. It is very akin to Plato. Nothing of this world and nothing of your thinking can bring you closer to reality. Once more is this echoed in modern times with this understanding of the universe, that we are literally not in it. We are floating about somewhere else, and our bodies cannot reach into anything real. We're actually quite a scary view. And of course, it doesn't become scary until you discover it. I think Westerners are used to being scared and traumatized since the Greek, and this is a healing thing. Above all, it's a healing thing. And I will argue in the next lecture that you can never ever heal as long as this grotesquely gigantesque problem is still around. it's in your system. The reason that we are today disembodied is the cosmology we're living with, and it affects us in every little thing that we do in our lives. I say thank you very much and have a very pleasant morning, which is still. Bye-bye. Mm-hmm.